So next is a topology. That is also one communication criteria where the different nodes are able to communicate. Among the access technologies available for connecting the IoT devices, there are three main topology schemes are dominant. One is a star topology, mesh topology, and peer-to-peer topology. So you can see there the dark circles and the gray circles, right? The dark circles identify the full function device, right? And the gray circle which you can observe on the diagram is a reduced function device. Okay. And for long range and short range technologies, we use a star topology is a prevalent. As seen with the cellular technology, low power wide area and Bluetooth networks, star topologies utilize a single central base station or controller to allow communication with the endpoints. The medium range technologies, a star, peer-to-peer or mesh topology is common as we have shown in the diagram. Peer-to-peer topologies allow any device to communicate with any other device as long as they are in range of each other. Obviously, peer-to-peer topologies rely on multiple full function devices. Peer-to-peer topologies enable more complex formations such as mesh networking topology. For example, if you take the indoor Wi-Fi deployments are mostly a set of nodes forming a star topology around their access points, APs. Meanwhile, the outdoor Wi-Fi may consist of mesh topology for the backbone of APs with the nodes connecting to the APs in a star topology. Similarly, IEEE 802.15.4 and 80G are even wired IEEE 1901.2a PLC are generally deployed as a mesh topology. A mesh topology helps to cope with the low transmit power, searching to reach greater overall distance and coverage by having an intermediate node relying on traffic for other nodes. Same. So you have seen the diagram that star topology, mesh topology, and the peer-to-peer topology, right? So mesh topology requires the implementation of layer 2 forwarding protocol known as a mesh under or a layer 3 forwarding protocol referred to as mesh over on each intermediate node. So IoT network architecture is a full function device, FFD, that is a full function device is simply a node that interconnects to other nodes. A node that does not interconnect or relay the traffic of other nodes is known as a leaf node or reduced function device, RFD we can call, okay, or as the last source. So for also presented. While well adapted to powered nodes, mesh topology requires properly optimized implementation for battery powered nodes. And these battery powered nodes, in case of mesh topology, either often placed at the sleep mode or preserve battery life when not transmitting. In the case of mesh topology, either the battery powered nodes act as a leaf nodes or as a last resource path to relay traffic. When used as intermediate nodes, otherwise battery lifetime is greatly shortened. For battery powered nodes, the topology type and the role of the node in topology, for example, being an intermediate or leaf node, are significant factors for successful implementation. So these battery powered nodes, role of the node is being intermediate and are significant factors for successful implementation. So another communication criteria is a constrained devices. That is, a constrained nodes have limited resources that impact their networking features, set, and capabilities. The Internet Engineering Task Force (IETF) acknowledged the request for commands. Request for command, that is RFC 7228, that different categories of IoT devices are deployed. The when while categorizing the class of IoT nodes is the perilous exercise with computing memory shortage, power and networking, continuously evolving and improving RFC 7228 that gives some definitions of constrained nodes. These definitions help differentiate constrained nodes from unconstrained nodes such as servers, desktop or laptop computers, and powerful mobile devices such as smartphones. Constrained nodes have limited resources that impact their networking features, set, and the capabilities. Therefore, some classes of IoT nodes do not implement in IP stack. According to RFC 7228, constrained nodes can be broken down into the classes defined, say into classes class 0, class 1, class 2. Okay. So when you take a class 0, the definition of this constraint node class 0 defined by RFC 7228 is this class nodes is severely constrained with less than 10 KB or memory or less than 100 KB of flash processing and shortage capability. These nodes are typically battery powered. They do not have the resource required to directly implement an IP stack and associated security mechanisms. An example of class 0 node is a push button that sends one byte of information when changing its status. This class is particularly well suited to leveraging new unlicensed low power wide area network and the wireless technology. Okay, those is the best suited new unlicensed low power wide area is a wireless technology. So this class is well suited for the leveraging new licensed low power wide area wireless technology. When you take a class 1 constraint nodes with RFC defined by 7228, while greater than class 0, the processing and code space characteristics approximately 10 KB RAM and approximately 100 KB flash of class 1 are still lower than expected for a complete IP stack implementation. They cannot easily communicate with nodes employing a full IP stack. However, these nodes can implement an optimized stack specifically designed for constrained nodes like Constrained Application Protocol CoAP. This allows class 1 nodes to engage in meaningful conversation with the network without the help of gateway and provide support for the necessary security function. Environmental sensors are the examples of class 1 nodes. Next, if you take a class 2 nodes, constrained nodes are characterized by running the full implementation of an IP Internet Protocol stack on embedded devices. They contain more than 550 KB of memory and 250 KB of flash memory, so they can be fully integrated in Internet Protocol networking. A smart power meter is an example of class 2 node. So when you come to the communication criteria with respect to the constrained node networks. So in this, what we are going to study is data rate and their throughput, latency and determinism, okay, overhead and payload. So communications criteria when you with respect to the constrained node, While several of the IoT access technologies such as Wi-Fi and cellular applicable to laptops, smartphones and some IoT devices. Some IoT technologies are more suited to specifically connect constrained nodes. Typical examples are IEEE 802.15.4 and GRF, IEEE 1901.2A PLC, LPWA, and IEEE 802.11AH access technologies. These technologies constrained networks are often referred to as a low power and lossy networks, LLNs we call them. So they why we call them as a low power and lossy networks, because in context with the LLNs refers to fact that nodes must cope up with the requirements from powered and battery powered constrained nodes, and these lossy networks indicate that network performance may suffer from a interference and variability due to harsh radio environment. Layer 1 and layer 2 protocols that can be used for constrained node networks must be evaluated in context of the following characteristics: for use case applicability, data rate and throughput, latency and determinism, and overhead and payload. Layer 1 and Layer 2 protocols that can be used for constrained node networks. Data rate and throughput. Data rates available from IoT access technologies like LTE. Throughput is less than the data rate. Short range, data range and the throughput. So the data rates available from IoT access ranges from 100 bits per second with the protocols such as to tens megabits per second with technologies such as LTE and IEEE. So these sometimes much less than the data rate. Therefore, understanding the bandwidth requirements of a particular technology, its applicability to give an use cases, the capacity planning rules and the expected real throughput are important for proper network design and successful production deployment. Technologies not particularly designed for IoT such as cellular and Wi-Fi match up well to IoT applications with high bandwidth requirements. For example, nodes involved with video analytics have need to for high data rates. These nodes are found in retail, airport, and smart city environment for detecting the events and driving actions. Because of these types of IoT endpoints are not constrained in terms of computing or network bandwidth, the design guidelines tend to focus on application requirements such as latency and determinism. Latency and determinism is discussed more detail in this. Short range technologies can also provide medium or high data rates that have enough throughput to connect a few endpoints. For example, if you take Bluetooth sensors that are now appearing on connected wearables fall into this category. The solutions focus more on a footprint and battery lifetime than on data rate. The IoT access technologies developed for constrained nodes are optimized for low power consumption, but they are also limited in terms of data rate, which depends on selected frequency band and the throughput. With a data rate ranging from 100 pps to less than 1 mbps, you may think of back to the years when bandwidth was a scarce resource. You often needed some expertise to understand how to design such networks. Today, this sort of expertise is helpful for low power wide area networks which are designed with a certain number of messages per day or per endpoint rather than just having the pure bandwidth usage limit. polling impacts on the design because all devices share the constrained bandwidth capacity. A discussion of data rate and bandwidth on the lossy uh, uh, networks must include look at a real throughput or throughput seen by the application. While it may be important for a constraint nodes that send only one message a day, real throughput is often very important for the constrained devices implementing an IP stack. Throughput is a lower percentage of the data rate even if the node gets the full constrained network in a given time. If you take example IEEE 802.15.4G 4G, right? So the cover border case of distance and radio signal quality, the will be turned on when lowers the data rate from 150 kbps to 75 kbps. If you now add in the protocol stack override, the two-way communication handling and the variable data payload size, you end up with a maximum throughput of 30 to 40 kbps. This must be considered as the best value because the number of devices simultaneously communicating along with the topology and control plane overhead will also impact the throughput. Another characteristics of IoT device is that majority of them initiate the communication upstream traffic toward an application server is usually more common than downstream traffic from the application server. Understanding this behavior also helps when deploying an IoT access technology such as cellular that is asymmetrical because the upstream bandwidth must be considered a key parameter for profiling the network capacity. So when you take a latency and determination, much like a throughput requirement, latency expectation of IoT application should be known when selecting the access technology. This is a particularly true for wireless networks where packet loss and retransmission due to interferences, collisions, and noise are normal behaviors. On the constrained networks, latency may range from few milliseconds to seconds, and applications and protocol stacks must cope up with these wide-ranging values. For example, if you take a unidatagram protocol at the transport layer, is strongly recommended for IP endpoints communicating over LLNS. When the latency is strong, in case of the mesh topology, if communications are needed between the two devices inside the mesh, the forwarding path may call for some routing optimization, which is available using the IPv6 RPL protocol. Okay. So when a latency is strong concern, emergent access technologies such as deterministic Ethernet or the time-slotted channel hopping mode of IEEE 802.1 should be considered. However, some of these solutions are not fully mature for production deployment. Okay. So overhead and payload, when considering the constraint across network technologies, it is very important to review the MAC payload size characteristics required by applications. In addition, you should be aware of any requirement for IP. The minimum IPv6 MTU size is expected to be the 1280 bytes. Therefore, the fragmentation of the IPv6 payload has to be taken into account by link layer access protocol with a smaller MTUs. The use of this internet protocol on the Internet of Things devices is an open topic, as we have mentioned that IETF acknowledges the fact that different classes of IoT devices exist. For the more constrained classes of devices like class 0, class 1 devices, it is usually not possible or optimal to implement a complete IP stack implementation. So for technologies that fall under lossy networks, constrained nodes, that is a two-way communication handling. Okay, so for technologies that fall under the LLN definition but are able to transport internet protocols such as the IEEE 802.15.4 and G and other IEEE standards which are mentioned capabilities or IP optimization is very important. The protocols which are IEEE 802 point some standards, right? The payload size of for IEEE this is 127 bytes and require IPv and IPv6 payload with a minimum of MTU of 1280 bytes of them to be fragmented. Okay. So most low power wide area technologies are offer small payload sizes. These small payload sizes are defined to cope up with the low data rate and time over the air and duty cycle requirements of IoT nodes and sensors. If you take example, payloads may be as little as 19 bytes using the low power area, wide area network technologies or up to 250 bytes. It depends on the adaptive data rate, while this does not preclude the use of IPv6 low warrant payload as in some of the endpoint implementations. So in conclusion, what we can say that communication criteria is just covered the fundamental to understanding the IoT access technologies, their characteristics when they are most applicable. These criteria should include the range, frequency bands, power consumption, network topology, the presence of constrained devices and or networks and data throughput. From the network engineer perspective, that is with respect to the Internet of Things, you must make sure an architecture is developed with the proper abstraction of the particular access technology. This is especially true for constrained network nodes where quite often your choices of protocols and solutions can be reduced or can be limited. Okay, so the main access technologies were dedicated to our constrained node networks. Okay, where we are going to use the the latency determination, payload and its size, okay, etc. So next we are going to study the IoT access technologies. That is a different IoT IEEE standards of these IoT standards. Different IEEE 802.1 standards.